Categorizing and classifying things seems to be a part of human nature. We group organisms into a number of different categories, such as kingdom, phylum, class, etc. Um, and when many different organisms have similar traits or characteristics, we group them together and we give that group a name. So, race is another example of this. There's no more genetic difference between a white person and a Hispanic person than there is between two white people or two Hispanic people. We've identified certain characteristics like skin color, which we use to group people together for better or worse. Chemical reactions are the same, and people have identified certain similarities between them that allow us to group reactions together. I'm going to go over some of the major types of reactions and some subtypes and how to classify a reaction into one of these categories. So the three major types of reactions are listed here: precipitation, acid-base neutralization, and redox. And I'll just jump right in and start by talking about precipitation reactions. So a precipitation reaction is one that produces a solid, and we call that solid a precipitate. Right? It's kind of like snow falling from the sky is precipitation. So same kind of idea here. The reactants in a precipitation reaction are going to be two dissolved aqueous ionic compounds. The products are going to be composed of at least one solid ionic compound, and the other ionic compound could be soluble. It could also be a solid. We sometimes call these double replacement or double displacement reactions because the cations and anions of the two reacting compounds are kind of swapping partners. So if you want to just look at a generic reaction equation for a precipitation reaction, this is kind of the general feature. The way it would look is you have some compound AB, where A is the cation and B is the anion, reacting with another compound CD, right? Similarly, C is the cation, D is the anion. And they're going to swap partners. So now the cation A is going to combine with the anion D of the other compound. And similarly, the cation of CD, which would be C, is going to combine with the anion of the other compound. And so for this to actually be a precipitation reaction, one thing that's not shown is that either AD or CB needs to be a solid. Okay, so AB and CD would have to be aqueous or dissolved. And what's going to happen is they're going to produce a solid. One of these compounds that gets produced over here on the product side will not be soluble. So some examples of precipitation reactions are, here we have silver nitrate, which is aqueous, right? We have a cation silver and anion nitrate. It's aqueous, so it's dissolved in water. And when ionic compounds dissolve in water, they split up into their ions. So the silver ions are going to be separate from the nitrate ions. We've got sodium chloride, which is similar, right? Sodium's the cation, chloride is the anion, and this is also aqueous, so it's broken up into its ions. And when the silver ions find the chloride ions, those are more strongly attracted to each other. And so it's going to end up, those are going to stick together. And as more silver and chloride ions kind of find this piece of solid, they're going to make bigger and bigger pieces of solid as all the silver and chloride ions start to stick together. You'll notice, so that's labeled as solid. Sodium nitrate is going to remain aqueous because sodium and nitrate don't have that super strong attraction. So in this case, we're forming one solid compound and one aqueous compound. Another example here, we've got barium nitrate and phosphoric acid. So even though phosphoric acid is not an ionic compound, acids, when they dissolve in water, produce H plus and some kind of anion. So here it's phosphate. So when you put barium nitrate and phosphate solutions together, the barium here is combining with the phosphate to form barium phosphate here. And the H plus is going to combine with the nitrate to form HNO3, so nitric acid. So again, you can kind of see how this relates to this generic equation where the cation of one compound and the anion of the other are going to combine and kind of swap partners. So then an example of a precipitation reaction is one listed here. So we have silver nitrate, and this time it's reacting with sodium hydroxide. So it produces silver hydroxide, which is an insoluble ionic compound. And In this video, you're going to see two solutions. So one solution is the sodium hydroxide solution that's in the test tube. So this is a zoom in of a test tube. And the silver nitrate solution is in the pipette that's in the solution here. So separately, they're clear, dissolved aqueous solutions, but the second they come into contact, you'll see that they start producing precipitate. Okay, and as they pour the silver nitrate or introduce the silver nitrate into the sodium hydroxide solution, they're going to react. So you can see the second that tip goes into the solution, the silver hydroxide starts to precipitate out and it forms that kind of like milky looking, gray-brown solid. So that's just one example of a precipitation reaction. The next type of reaction that we're going to talk about is the acid-base neutralization reaction. So a key feature of an acid-base neutralization reaction is that you've got H plus being transferred. So an acid is something that donates H plus, and a base is something that accepts H plus. So your reactants have to be an acid. So typically we identify these as compounds that start with hydrogen. Usually that indicates that they're acids. And a base. So bases are hard to identify because there's many of them, and they aren't as clearly distinguished as acids. But so for now, we'll just limit it to hydroxides. So any ionic compound that has hydroxide, that hydroxide is a strong base. So sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth. Did a little weird thing here with the formatting. Anyways, products, you're always going to form water when hydroxide is your base. So water is always going to be a product that we see in our acid-base neutralization reactions. And the other thing you're going to see is an ionic compound. In chemistry, a lot of times we call this a salt, but really that's just another word for ionic compound. We're not specifically talking about table salt, right, like sodium chloride. So a salt could be anything. It could be calcium chloride or anything like that. Okay, so again, we'll look at a generic reaction equation. We have HX, which would be our generic acid. We have MOH, so our generic base, right, where M is some kind of metal cation. And we've got our hydroxide here. They're both dissolved. And when they react, they're going to produce water, H2O, which is going to be a liquid. And one of the other products is going to be this salt, right, so MX. So these actually also, we talked about double displacement reactions. Acid-base neutralization reactions are also sometimes called double displacement reactions because the hydroxide here, the anion of this compound, is combining with the H plus that's coming from the acid, and our X is going to combine with the M of our hydroxide. Right, so it's kind of the same thing. We're still swapping partners, but here we're just dealing with specifically an acid and a base, and H plus is getting transferred between the two. Some examples here, we've got hydrochloric acid reacting with sodium hydroxide. We got H2O, like we said, and sodium chloride. Phosphoric acid, so 2 phosphoric acids, 3 calcium hydroxides, 6 H2Os, and calcium phosphate is our salt that we're producing. So again, here's a case where this ionic compound is solid, and also we've got a little bit different ratios here in terms of the coefficients on our reactants and products. Okay, one more, potassium hydroxide, sulfuric acid forming water again, and potassium sulfate. Now I didn't have a video to show of the acid-base neutralization reactions because they're actually usually not that exciting. So most acids are clear aqueous solutions. Or form clear aqueous solutions. Most bases form clear aqueous solutions. Water is obviously clear. Most of these salts are clear. So they aren't really all that exciting to watch. They do generate quite a bit of heat, and so you do have to be a little careful because sometimes you can add them, mix them together, and they'll produce a lot of heat, boil, and then you've got boiling acid and base, and that's not fun, huh? Anyways, moving on to the third type, so this is the third major type of chemical reaction that we're going to talk about, is a redox reaction. So the key feature here in a redox reaction is that electrons are going to be transferred. So in our acid-base reactions, we have H+, so hydrogen ions being transferred between two substances. Here we have electrons being transferred. And the term redox actually comes from a combination of two different words. Reduction, which is the gain of electrons, and oxidation, right? If something's gaining electrons, those electrons can't just come from nowhere. Um, the electrons have to be lost from something else. So when you combine these two words, you get redox, right? So that's where that comes from. You can identify a redox reaction whenever there is a change in oxidation state of atoms or elements. Okay, and there's going to be more on that. We'll talk about that in just a second. Within redox, redox is a really broad classification of reactions. So kind of like right, mammal is a really broad classification for organisms, right? There's many kinds of mammals out there. There's many kinds of redox reactions, and we're going to talk about 4 here. Synthesis or combination, those are 2 names for the same type of reaction. Decomposition, single replacement, and combustion. So the first thing we need to be able to do is know what an oxidation state is and how to identify an oxidation state. So an oxidation state is an estimate of the charge on different elements in a compound. So it's kind of like the formal charge we talked about when we were drawing Lewis structures. Formal charge is a fairly good representation of charge in covalent compounds, covalently bonded compounds. Oxidation state is a good estimation of charge on ionic compounds. And again, both of them are not terrifically great. Oftentimes, we're just trying to keep track of electrons when we're talking about formal charge or oxidation state. So for oxidation state, the real importance of it is here on the second bullet point. So we want to be able to identify when electrons are transferred from one substance to another, and we do that by looking at the oxidation states of the elements in those compounds. So we have some rules for identifying oxidation states. The first one is that the sum of the oxidation states in a substance should always add up to the overall charge. So if I'm dealing with a neutral compound, all of the oxidation states in that compound should add up to 0. If I'm dealing with something like a polyatomic ion, the sum of the oxidation states should add up to the charge on that ion. The next rule, here we go, is that monoatomic ions, so things like nitrogen 3 minus, right, nitride, or iron 3 plus, Fe3 plus, Fe3, those will always have an oxidation state equal to their charge. So like nitride, N3 minus, will always have a -3 oxidation state. Iron 3 plus will always have a 3 plus oxidation state. So that's pretty straightforward. Oxygen always has an oxidation state of -2, so that's kind of always a given, as long as it's in a compound. And we'll see why that's important in just a second. Hydrogen always has an oxidation state of +1, and again, only when it's in a compound. Okay, but those are 2 rules, rule 3 and 4 here, that are almost universal. There are very few exceptions to those rules. The reason we specify that oxygen and hydrogen have those oxidation states when they're in a compound is that all elemental substances always have an oxidation state of 0. Okay, so elemental oxygen gas does not have an oxidation state of -2. It's actually 0 if it's an elemental substance. And the last one, and this is kind of an iffy one, the halides are usually -1. And I know nobody likes to have rules that use words like usually or that kind of vague language, but it can be useful sometimes. But really, rules 1 through 5 are the ones that you use most often, and there are very few exceptions to those rules. Some examples. So if we're looking at sodium chloride, that's made up of two monoatomic ions, and so their oxidation states are just going to have the charge equal to their the oxidation state equal to their charge. So sodium is going to be a 1 plus ion, chloride is going to be a -1 ion, and that's just it. Carbon dioxide, the rule that we're going to invoke here, first off, is we can look at oxygen, right? We don't really have a rule for carbon, but we have a rule for oxygen. So oxygen is always 2 minus or -2 when it's in a compound. So in this case, oxygen is going to be -2, and since we have 2 of them, that adds up to 4 minus overall. So in order for our 1 carbon to balance out these 2 oxygens that are each -2, we need to have a carbon that has a +4 oxidation state. So we can't immediately know what carbon is, but we can figure out what carbon's oxidation state is from the oxygens. And this is a lot of times what we're going to do. So we're going to use our rules, the rules that we have, to identify the oxidation state in one or two of these elements, and then we can use that to find the oxidation state of the other elements in the compound. H2S, here again are the rule we can invoke. We don't know about sulfur. That can be different oxidation states. That can have different oxidation states. But hydrogen is always +1 in a compound. So we know that. And if that's the case and we have 2 hydrogens, then sulfur has to be -2 in order to balance that out. Sulfate, now this is a polyatomic ion, so the oxidation states have to add up to -2. So here I've got 4 oxygens. Oxygen's always -2. And overall, this has to add up to 2-, and I've got 4 of these 2- oxygens. So that adds up to 8-. So in order for it to all balance out to 2-, if I have a total of -8 from the oxygens, I need sulfur to have a +6 charge. Okay, so sulfur is going to have an oxidation state of +6 here. O2, this was one of our examples. O2, since it's an elemental substance, it just has one element in there, and it doesn't have any charge, you can't have any oxidation state here, or you can't have any non-zero oxidation state. It has to be 0. Oxygen, if it were 2-, right, we'd have 2 2- charges, and that would have to be a 4- polyatomic ion or something like that, and that's not the case. CCl4, so here's one where carbon we don't really know. Chlorine actually can change, and we'll see that when we do examples, but Cl here we're going to assume is -1 because we don't really have much else to go off of. And we have 4 of them, so carbon here has to be +4 in order to balance that out. Okay, so that's how we kind of identify oxidation states and some examples of all of the important rules, all the 6 rules that we talked about. So now we can use these oxidation states, right? How do they relate to redox reactions? Well, we can identify the oxidation states for each of these elements in a chemical reaction in each compound or substance and see if they change going from the reactants to the product side. Oops. So here we're going to start with carbon and, methane. So hydrogen's always +1. Carbon then has to be -4 in order to balance out those 4 +1 charges. Oxygen is always 0. And we'll look at the products now too. So here oxygen is -2. We've got 2 of them. We already talked about carbon dioxide. Carbon has to have a +4 charge. Here hydrogen is going to be +1. We have that rule. There's 2 of them. We also have the rule that oxygen has to be -2, so we just know that. And so you can see here, hydrogen is not changing oxidation state. It's +1 on the left side, it's +1 on the right. But if we look at oxygen, oxygen as an elemental substance has an oxidation state of 0, and over here it has an oxidation state of -2. Okay, so we say that oxygen is getting reduced. So, yes, oxygen is getting reduced. Had to check that. Because it is gaining electrons. And we say it's getting reduced. That might seem weird. Why would reduction be a gain of electron? But you know that it's getting reduced because the charge is decreasing, right? It's becoming more negative. It's going from 0 to -2. So that's why we call it reduction. So yes, this is a redox reaction, and we can identify, right, if oxygen is getting reduced here, we immediately know that methane must be getting oxidized. Okay, and we can see this because carbon's going from -4 to +4. Okay. Another example here, we've got this silver nitrate and sodium chloride reaction. If we look at the oxidation states here, so nitrate is a -1 ion, -1 polyatomic ion. Oxygen's always 2-. We've got 3 of them, so that's -6. So nitrogen then has to be +5, right? Because nitrate is a -1 ion. Silver we know is going to be +1 because silver is a monoatomic ion. It always takes that +1 charge. Okay, so nitrogen's +5, silver's +1. We already did sodium chloride. Silver chloride similarly is monoatomic ion, so it's going to be -1 and +1. And sodium nitrate here, again, one thing you'll notice is that when you have a polyatomic ion that doesn't change from one side of the reaction to the other, it'll have the same oxidation states. right? So if we look at nitrate again over here, we're going to get the same situation where oxygen's -2 and nitrogen's +5, and sodium's +1 here. So you'll notice here, sodium's +1 here, it's +1 here. Chloride is -1, it's -1. Nitrate has the same oxidation states from the left side to the right side. Silver has the same oxidation states from left to right. So there's no change in oxidation state, so it is not a redox reaction. So what type of reaction this is, right? We can identify, right? Two ionic compounds swapping partners to form a solid. That's a precipitation reaction. So that's not a redox reaction. Okay? So that's just the way we use oxidation states to identify redox reactions. Going into those different subtypes that we talked about, synthesis or combination reaction, this is any kind of reaction that has two or more substances actually combining to form a single product. So the generic equation here is A plus B goes to AB. So two things combining to form one. You could have more though. It could be A, B, C, D, E, all combining to form one compound. So some examples here. We've got sodium metal reacting with chlorine gas, and we've got sodium chloride. So you'll notice here we've got a plus because we have two different substances on the left side of the reaction, and on the right side, on the product side, we just have a single substance. Okay, and you can identify the oxidation states of these compounds if you want, but I'm just giving it to you that they are redox reactions. Another one here is carbon and oxygen. So carbon is a solid. Oxygen gas is a diatomic gas here, and when they combine, they form CO2. Okay, so two things combining to one. An example here is sodium reacting with chlorine. So this is actually one that we would not do probably in a high school chemistry lab because it's pretty dangerous. Chlorine is like really nasty stuff. They used it in World War I as a chemical warfare agent. Sodium is a nasty metal that explodes when in contact with water. So we're just going to listen to it. And this guy has like the driest voice in the world. Although maybe you think my voice has been pretty dry in this video, but I think he'll probably take the cake. So I'll just hit play here.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas.
Who wouldn't love chemistry? Listen to this guy's voice all day, right?
The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
Boom. So actually this white powder that you're seeing here that quickly forms, the reaction generates so much heat that it actually vaporizes some of the sodium chloride. And when the sodium chloride hits cooler air above it, that actually immediately condenses into a solid. So you're seeing like little tiny particles of sodium chloride that are condensing into, well, I guess they're depositing into solids in the air. So that's just an example of a synthesis reaction. Decomposition reaction, pretty straightforward. It's just the opposite of a synthesis or combination reaction. So when you have one thing and it breaks into many things. The generic equation here is AB goes to A plus B, right? Pretty straightforward. Examples, sodium chloride, so the opposite of what we just saw here. So sodium chloride can get split into sodium metal and chlorine gas. This is actually how they generate sodium metal and chlorine gas. These are both very reactive elements that don't exist as pure elements in nature because they're so reactive. They want to react with anything around them. So the way they do this, which is, it sounds really dangerous, they melt sodium chloride, which has to get up to like 800, between 800 and 1,000 degrees Celsius. They run some electricity through that liquid, and the electricity causes the electrons to go back from chloride into the sodium. And that's how you end up getting sodium and chlorine gas. So that's actually how they commercially produce these things. Sounds like a very dangerous process. Another one is iron. So if you actually take iron that's rusted, so this is the formula for rust. If you heat that up really hot, it'll actually force the oxygen out of the rust, and you end up with iron and oxygen independently. So again, both of these things are taking one thing and producing more than one thing. Nice example here is our ammonium dichromate volcano. All right. So one substance here, we have ammonium dichromate. It's a ionic compound, not a very stable one though. The oxygens on chromium, right? Chromium's got a lot of oxygen bonded to it, and actually that oxygen wants to escape. And having ammonium there gives it a lot of hydrogens that are close by to produce water. Okay, and you also can produce nitrogen here. Nitrogen and water are really stable compounds, and they're both produced as gases because this reaction releases a lot of heat. We're still left with chromium 3 oxide here. But yeah, anytime you're forming really stable compounds like this, it'll end up being a very vigorous reaction. So let's watch this happen. It takes a second to really get going here, but once it's going, you can see why they call it the volcano. Now you'll notice it's making a lot of these really tiny little particles here. That's because of all the gas that's getting produced, right? We've got a mole of, every time a mole of this reaction happens, we're getting a mole of nitrogen gas and 4 moles of water gas, or water vapor. And so because of that, it ends up making it so big chunks of solid can't form here. All right, that's a nice one. Cool. All right, shifting gears, or not shifting gears, but moving on to the next one, single replacement reaction. This is any reaction where one element is replacing another element in a compound. So here we have, let's say, some ionic compound, for instance, Bc. And depending on what element, A, we introduce here, we could replace either the cation, B, or the anion, C. So here I have it replacing the anion, C. So here we have our A, our element, replacing C in this compound to form AB and C. Or we could have A replacing the cation. So this is actually more common, where we have A replacing B to form AC and leave B as an element on its own. So some examples here are lithium. Lithium is actually a very reactive metal and will replace other metals. So if I take lithium metal and I put it in a solution of aluminum chloride here, it'll replace the aluminum. I'll end up getting aluminum, or solid aluminum, coming out of the solution, and we'll be left with lithium chloride instead. Another example here, cesium chloride reacting with fluorine. Fluorine's one of the most reactive substances out there. Fluorine will very much like to replace chlorine or chloride in this compound. And so what you have is exactly that happening. So we're left with cesium fluoride and chlorine gas. Here's an example of a reaction. Here we have iron reacting with copper sulfate. So the copper will actually replace the iron. And when it does that, so what we have here, actually, once I get this going, is we have two kind of wires of iron, and they're in a solution. That greenish solution is the copper sulfate. So the copper is going to actually come into contact with the iron metal, and it will turn into a solid at the surface, and so you get these cool crystals of copper forming all over the surface of the iron. You'll also notice that the green color of the solution is going to kind of fade away as the copper deposits here on the metal. And iron sulfate is one of the things we're going to form, right? Iron is replacing copper in this compound. Iron is actually not going to have a color in the solution, so it'll actually make the solution clear. Oops, I got to hit play here. Right, so you can see the green color of the solution as this proceeds starts to fade, and we get these really nice red copper crystals that start to form and flake off. So this is obviously, you can tell it's kind of zoomed or fast forwarded time lapse of this reaction. All right, moving on. The last one we're going to talk about here is a combustion reaction. So a combustion reaction is any reaction where you take a substance and react it with just elemental oxygen. Most commonly, what we're going to see is compounds containing carbon, hydrogen, and maybe oxygen with some kind of ratios here, X, Y, and Z, that are going to react with oxygen. And in this case, oxygen is just a really reactive compound. And so it's going to try to stick to carbon and hydrogen as much as it can. The most it can do is form these two compounds here, carbon dioxide and water. So, things like cellulose in wood is composed of carbon, hydrogen, and oxygen. When you burn them, you end up getting CO2 and H2O being produced. So some examples here, we've got methane gas reacting with oxygen. We're getting CO2 and H2O. And based off of the formula of the compound you're combusting, we're going to get different ratios of these substances here. Okay, here we've got pentane, I guess I'm not sure exactly what the name of this compound would be, but another compound containing carbon, hydrogen, and oxygen reacting with oxygen to form CO2 and H2O. I guess I haven't balanced that one. Here's an example of a different kind of combustion reaction. Oops. So even though the ones we'll typically see are going to be hydrocarbons or things containing carbon, hydrogen, maybe oxygen, combusting, we also have other types of reactions. So again, a combustion reaction is just one where a substance reacts with only elemental oxygen. So here is an example of iron reacting with elemental oxygen to form iron oxide, in this case iron 3 oxide, which is rust. You don't really think of iron as being combustible, and it won't usually. You can't really light iron on fire. What we have in here in this Erlenmeyer flask is pure oxygen. So they actually created pure oxygen gas and filled this Erlenmeyer flask with it. And actually, if you take something like steel wool, which has really fine, wires of iron, that actually does have enough contact with the oxygen gas to combust. And when you put it into pure oxygen gas, then you actually can get a pretty good combustion reaction going on. So let's do this. Right, pretty quickly that thing will catch on fire. Oh, hi, Obama. And turn into iron oxide. Okay. So just to recap, we've got 3 major types of reactions that we can classify. So the first here is precipitation, where we have 2 ionic compounds swapping partners. One of these has to be a solid in order for it to actually form a precipitation reaction, for it to precipitate. We have an acid-base neutralization reaction, an acid and some base. What we're going to talk about is hydroxides as our base to form water and some kind of ionic salt. We have a redox reaction, and actually we have many types of these redox reactions, right? We have 4 types. So synthesis and combination, these are reactions where you have multiple things reacting to form a single thing. Decomposition, we have one thing decomposing into many things. Single replacement, we have an element that is replacing an element that's within a compound, right? A replacing C or A replacing B. And a combustion reaction is one that reacts with oxygen. Again, we saw that one where we had iron combusting, but usually what we're going to have is carbon, hydrogen, oxygen reacting with oxygen to form CO2 and H2O. All right, so I hope that was helpful. Please feel free to reach out to me with any questions. And yeah, you'll definitely have some chances to practice this. All right, thanks.